Hello there, our wonderful and esteemed viewers on this favorite mathematics YouTube channel, Mathematics by Abu Zainab. That special channel created for you and I to come together to demystify mathematics and tackle the age-long phobia associated with this all-important subject, one topic at a time. Thanks so much for staying tuned and being loyal subscribers. Today, which promises to be another interesting, exciting, and yet fun experience in learning mathematics, we are continuing in the topic we started in the last video, which is probability distribution. In the last video, we introduced the concept of probability distribution, and we mentioned the two broad categories of probability distribution, which are discrete and continuous. And we didn't mention examples of discrete to include Bernoulli, binomial, and Poisson. And of course, we made a classic example of continuous, which is normal or Gaussian distribution. Our focus is going to be on the discrete, and specifically binomial and Poisson. And we started the last video with looking at the properties that must be met for a random variable to be deemed called the binomial distribution. And for sake of revision, these properties are as follows. One, there must be n fixed number of trials, and each trial must only have two possible outcomes, which I mentioned as success or failure. And each success is given with probability P under case P. And lastly, that each trial is independent. So if any random variable possesses these four conditions or criteria, then we call that binomial probability distribution. So today we are going neck deep into the computations involved in this important distribution, binomial distribution, with the example on the board. We've got that if 20% of memory cards produced in a computer manufacturing company are defective, determine the probability distribution of defectives in a random sample of 5 memory cards. This is a typical question. The major headache in an exam for students is to identify what distribution is this problem really. It's full of words. However, we are not left alone. We have to look at those 4 criteria. We run this question through those 4 and determine if indeed it's binomial distribution or not. To start with, for binomial distribution, there must be what n fixed number of trials. So in this case, our n is actually 5. 5 random samples. So we have n equals 5. And we are told that 20% of memory cards are defective. So that means the word defective here represents the success. And that means the small p will be 20%, which is 0.2. That's our small p. So then we can now conclude that, okay, is there you have defective or non-defective? These are 2 outcomes. That's condition 2. Condition 1, there are n, which is 5, fixed number of trials. 2, there are only 2 possible scenarios here. Either you are defective or not defective. Of course, if it's defective, probability is 0.2. Then 1 minus p will be 0.8. That's 1 minus 0.2. And again, each outcome is independent of the other. And this probability of success in each case is always 0.2. So if 4 conditions are made, hence we can conclude that this is a classic example of binomial distribution. If that's the case, then what is our P? X equals to X. Probability of an event there is given as simply n combination X, P of X, then 1 minus P, n minus X. So in this case, X runs from 0 to 5, because the n is 5 here. Now, this question is asking us for the probability distribution of defectives. In other words, we are asked to get the full picture in tabular form, preferably, for each x and the corresponding probability. Remember, that is the definition of probability distribution given the last video. Each random variable, which is x in this case, along with the corresponding probability. So, we are going to take each of the x's 0, 1, 2, 3, 4, 5 and compute their respective probabilities. And that's all. So to start with, probability of x equals to 1, sorry, x equals to 0, because we start with 0. Now it's a 0 defective. That's going to become, just substitute n is 5, combination 0, then p is 0.2, raised power 0, and 1 minus p is 0.8, raised power 5. That is, for x equals to 0, we're going to have this. When you compute in the calculator, you're going to have 0.32768. The probability x equals to 1. We're going to have 5 combination 1. Just substitute. Then 0.2 raised power 1, 0.8 raised power 4. So when you compute that, you're going to have 0.4096. That is for x equals to 1. Now for x equals to 2, we're going to have likewise 5 combination 2, 0.2 raised power 2, then 0.8 raised power 3. So that is going to be 0.2048. Then we move to when x is actually 3. So we have 5 combination 3, 0.2 raised power 3, and 0.8 raised power 2. So then we have 0.50512. 0.0512. And when x equals to 4, we're going to have 5 combination 4, 0.2 all raised power 4, 0.8 to the power of 1. So when you compute that in your calculator, you're going to have 0.0064. And lastly, when x is equal to 5, we have 5 combination 5, then 0.2 to the power of 5, of course 0.8 to the power of 0. And that gives 0.00032. So these are the full probabilities of respective outcomes when x assumes the values 0, 1, 2, 3, 4, 5. Now, a very quick safe proof test to know if you are right is that when you sum up all these probabilities from 0 up to 1, you must necessarily get 1.0000, which indeed shows that it's a probability distribution, because the summation of probability distribution for discrete is equal to 1. Whereas if it's for continuous, it's going to be the integral value will be 1 as well. And of course, in no element probability, the maximum you can have, which is the probability of the sample space, is 1. So that indeed shows that these values are correct. And with that, we've actually solved the question. The probability distribution for 5 memory cards will be respectively, for 0, we have this, for 1, we have that, for 2, we have that, for 3, 0.0512, for 4, 0.0064, and for 5, we have 0.00032. And that has been our lesson for today, which promises, I believe, to be as interesting as you expected really. So, we are going to move deeper again into other categories of questions, still on probability, on binomial probability distribution next video. So I enjoy you. So please stay tuned, subscribe, like, share, and most importantly, tune on your content so that you'll be the first to know when the next video shall drop. Thank you and stay blessed.